Hey everybody, hope everybody's doing good. We'll pull our class up here. So on Monday, we talked about a whole lot of conversions between different numbering systems, decimal, binary, octal, hex. Then we got into, we also talked about, went back and reviewed gates and looked at our different gates, looking at digital logic and the output of those gates based on inputs, kind of looking at the Boolean expressions and looking at the truth tables, being able to recreate those truth tables. And so we're going to take that, those building blocks of, being able to, that combinational logic, being able to combine different gates together. We're going to take those basic building blocks, and then we're going to take one step forward, and we're going to look at tonight what we're going to call flip-flops, and we'll see why they're called flip-flops or latches, as we get into these devices. And so it's really about taking one more step and being able to hold in place this data. We're talking about data transfer, data communication, and being able to move these bits. And we talk about binary and these binary bits represented by these different levels of voltage, trying to move those and over a communication medium, but then also locking them in and having some type of memory device. And that's what we're going to talk about tonight as we look at flip-flops. So let me go ahead and share the presentation. By the way, before I do that, how did you guys find the last, I gave you guys probably about 30 minutes last class to go out and go through some of the quizzes, utilize some of that time to go back and review. Was that beneficial or was that not?
I think it was beneficial.
Okay.
That was.
Okay, just good to know. Good to know. I didn't have anybody come back and say, hey, I've got questions or anything. I kind of just hung around till the top of the hour. But yeah, good to know if that's beneficial or not as we continue to move forward. There'll be a couple sessions where we may have some time, and if that's helpful, then we may do that in the future. If it's not, then we can do a couple other things as well. All right, so let's share this presentation. You guys see that flip-flops?
Yeah.
Okay. So really what we're going to do is we're talking about these flip-flops, and you guys will see as we get into looking at our first flip-flop exactly what we mean when we're moving from gates to these flip-flops, because these flip-flops are made up of what we talked about, these gates. And so it's a matter of taking those gates and putting them in a proper sequence to get the flip-flop, and then the flip-flop will accomplish these tasks of being able to hold a signal. A couple of things that we're going to talk about that's a little bit unique in terms of flip-flops versus what we saw with gates and just building on gates. First is this notion of a timing chart. We're going to see that these flip-flops have a activating signal. They have a way of making sure that they are timed together. And so we're going to look at that signal and look at how we trigger these flip-flops. We're going to look at some of the logic symbols of different types of flip-flops, and we're actually going to go through and look at the input on a particular flip-flop, and what does that mean for the output of that given flip-flop. And then at the end, we'll see a Schmidt trigger, which is, takes a sine wave and turns that into a square wave. And so by the time we get there, we'll have a little bit better understanding as to why we need that device. So first of all, I mentioned that these devices, these flip-flops, they're triggered, right? They're sequenced, if you will. There's a signal that we're going to use, a clock pulse that we're going to use to make sure that if I have multiple flip-flops, that those flip-flops are all sequenced together, right? They're timed together. And so one of the things we have to look at first is this signal, and how do we trigger these devices, and even in terms of what we've been talking about in terms of high and low, what is a high and what is a low. And so here we've got really a couple different things that were being shown by this this chart, this signal here. First of all, you can see that I've got two square waves, and I've got one that's labeled on the top as positive logic, one that's labeled as negative logic. We're really going to focus on positive logic as we move forward and look at flip-flops. However, the difference in the two, basically, if we look at A here, right, we see that A is a logic 1. Well, the most positive voltage for positive logic is going to be a 1. The difference with negative logic, the most negative voltage is still a 1, right? And so it's really the same thought process in terms of the greater the value, the is going to be a 1. The lower the value is going to be a 0. It's just that with this negative logic signal, it's going in the opposite direction. It's going more negative. Now you can imagine that to keep things easy for us to understand, imagine that this line here is at 0, right? And so this is some negative voltage, say -5 volts. This is 0 volts. Well, -5 is going to be a 1. 0 volts is going to be a 0 or a low. It could be different. It could be different voltages, but that just helps us think about, all we're saying is the more negative voltage for negative logic. We're going to focus on positive logic. Positive is the same thing. Imagine that this is sitting at 0. Imagine this is 5 volts. So positive 5 volts is going to be my 1. 0 is going to be my low or my 0. And then I'm going to use this as my clock signal. So I've got my high at A. I've got my low at B. So we're just looking at this positive logic. You can see how higher voltage drops down. This is going to be a 0 at a lower voltage. And keep in mind, we're using this one square wave to demonstrate all of these different pieces. So it looks like there's a whole lot going on here, but we're just showing you the difference between a high and a low, and then we're showing you the difference between leading edge versus lagging edge or trailing edge, right? And so when we have these flip-flops and we want them to all trigger at the same time, what we're going to do is we're going to use a clock pulse, a square wave, and I'm going to have it triggered. And I could have it triggered on the level, meaning up here at a high or a low, or I could have it triggered on the edge, leading edge or lagging edge. Now, it's better to have it triggered on the edge, because see how precise this is? I go from 0 to a 1, And if I'm looking at triggering this flip-flop on the leading edge, all of them are going to be synchronized by this change from 0 to a high, 0 to a 1, with this quick change, this edge. That's typically what we're going to do, is we're going to use the edge to trigger. You could trigger on the level. The problem with that is you may be at a 1 for an extended period of time. It goes to a 0. Maybe you're going to trigger here. You could have multiple flip-flops and they could get out of sequence, right? They could not trigger exactly at the same time. And so it's always best if you can get them as precise as possible, as close to each other as possible. And so why not trigger off this one signal and trigger off this leading or lagging edge? Now, right now, all I want you to really see, because some of this is going to make more sense once we get a couple more slides in, dealing with positive logic. High is 1, the most positive voltage. The least positive voltage is going to be my 0. And then I have a leading edge and I have a lagging edge. Here, once again, we're looking at this up clock or down clock. All we're saying there is the transition. Is it going from a low to a high? In other words, is it right here? It's going from a low, my least positive voltage, to a high, my most positive voltage. And so if it's going from low to high, then that's going to be my up clock. Down clock was what we saw with the lagging or trailing edge. I'm going from a logic 1, my high, to a low, my most positive voltage, to my least positive voltage. And so I could trigger there as well. Usually we're going to trigger right here with this leading up clock. Okay. This is just showing what I was saying about you could trigger on, the leading edge. You could trigger on the lagging edge, or you could trigger on the level. Like I said, most of the time we're going to be better off to trigger on the edge, and we're usually going to stay right here with the leading edge. When we have that up clock going from a low to a high, then we'll have our flip-flops trigger, and it will cause the actions that we're going to see really starting next slide in terms of how these flip-flops are then going to hold hold a signal in place, if you will. All right, so let's kind of dive into flip-flops and what are they. If you look on the right side, we have the schematic symbol at the bottom, and this is going to be our RS flip-flop. All right, this is it looks like a square or looks like a rectangle. We've got inputs, we've got outputs, and what it's really made up of, the way it's wired, if you will, is these gates. All right, and so we see here that we've got two. Anybody remember what type of gates these are?
It's not and or.
Yeah, so in terms of just this, they're both the same type of gate, but this gate, and you can barely see this bubble inverter on the outside, right? And so it looks like an AND, but it's got the inverter. And so we said that this is a NAND gate, right? And so we had two NAND gates. And you can see the way they're wired up. I've got an input on the top NAND gate. I've got an input on the lower NAND gate. And then I've actually got an input that's connected to the output of both of those NAND gates, right? One's connected to the output of the top. The other's connected to the output at the bottom. And we're going to see what happens here. We're going to see, what would happen with this RS flip-flop, right? This is an RS flip-flop, right? And it says it's a bistable multi-vibrator, which means that it can be only one of two states, right? It can change. It can go from one state or the other, depending on the input, but it's only going to be one of two of those states. And then it's going to, once we set it, it's going to hold that state until we change it, right? Until we do something to cause it to change. And so what that means is that this RS flip-flop can hold, it's only holding one bit, right? It's holding either a high or a low, a 1 or a 0, but it can hold it. And for as long as we need it to hold that particular state. And, if you think about getting a lot of these flip-flops together, you can begin to put together enough flip-flops where you can hold multiple bits or multiple, even bytes, if you will. And so you go from flip-flops and you begin to build other devices called registers. Oh, one sec. So I was logged out. I just want to. You guys still there?
Yep.
All right, good deal. Let me go back to. All right. So here we are, RS flip-flop. So we can hold this state. Once we set it, all right, we can hold it. Now let's talk about some of the inputs and outputs. First of all, the inputs, S and R, right? RS flip-flop, real easy to remember in terms of what these inputs are. S, set, R, reset, right? And the best way to think about that is that when I have set, when I have an active input on set, that's going to give me a 1 on Q. All right. So if I set Q, if I set the output is going to be a 1. Now, if I have my outputs of Q and Q naught, well, if Q is 1, then that means that Q naught is going to be the opposite state, right? So if Q is 1, Q naught is going to be a 0. My input of reset, when reset is active, reset is going to clear Q, right? And so it is now going to cause Q to be a 0. Well, if Q is a 0 with an active input on R, then that means Q naught, the opposite, is going to be a 1. Right? So if I set it, I get a 1 on Q. If I reset it, I get a 0 on Q. Now, the trick here is we look at these inputs and outputs. What can you tell me about set and reset? You see anything that's different about set and reset? Anything that's I mean, it's unique. It's familiar from our discussion about gates. But what do you see on set and reset input? See this little circle? We often called it a bubble inverter on the output. Like for NAND gate, we said this was a bubble inverter, and it's still an inverter, But what I like to think about in terms of input, when we see this on the input, we'll often call this a state indicator. What that means is this is going to be an indication as of what input I need here for this input to be active. For example, since I've got a circle here, I've got this state indicator. This means that set is going to be active when I have a 0. Right? I get a 0 on my S. I get a 1 on reset. Well, S would be active. Set would be active because it has a 0 and the state indicator is indicating that it is active low, right? So a 0, a 1, that's going to be an active set, which means I get a 1 out on Q. I'm setting this RS flip-flop. Setting means that I'm giving Q is going to be a 1 out, an output of 1 or high. Let's take a look at what this input chart would look like. Here we have my RS flip-flop. Looks exactly the same. Set, reset, Q, not Q, or Q not. We said that set was active low, reset was active low. So let's just look at those first. All right, so if I go to set, where I've got a low on S, that's active. I've got a high on reset, so that's not active. And so since set is active, I should expect a 1 on Q. And so I get a 1 on Q, and the opposite on Q, not. If I look at reset, my input S is a 1. Well, it's active low, so that means that this is not a set. This is it's not active. R is a 0. Well, R is active low, so it is active. Active reset. I'm resetting Q to 0, so I should get a 0 on Q and a 1 on Q not. I can also get a high or a 1 on set, 1 on S, a 1 on R. Both of those are active low, and so therefore neither are active because I've got a 1 and a 1. All that does is basically says keep whatever you had. All right, that's gonna hold whatever the previous state was. Right, and so if we had, let's say we had a Q was a 1. We just had a reset. I mean, just had a set. So Q was a 1. And then we get a 1 on both R and S. Well, Q is going to remain 1 until one of these inputs go active. As long as they're both inactive, both high, Q is going to remain 1. And so you can see that we can basically lock in a bit, right? Imagine that we were dealing with those binary bits, those 1s and 0s, and you know, whatever data that might have been. Well, we can lock in a bit, either set it or reset, so we can get a 1 or a 0, whatever we need, and then we can hold for as long as we need by keeping both of these inputs inactive or having a high on both of those inputs, and I'll have the output for as long as I need it. Now, the one state that we skipped over is if I have a 0 on S, meaning that it is active, and I get a 0 on R, meaning it is active. So set is telling Q to be 1, reset is telling Q to be a 0. That's really a prohibited state. Right? That's a state that's not going to provide a output that we can count on, right? I mean, sometimes we may get a 1 on Q, sometimes we may get a 0 on Q, we don't know, right? We don't know what's going to happen there. And so we say that is a prohibited state. And so we take precaution to avoid both of these being active. Now, I will say that in terms of flip-flops, RS is, I hate to say it's the simplest because, you know, it's not like the others are much more complex, but it does have the least number of inputs, and therefore this prohibited state, we don't have an opportunity to avoid this state as much as we will see with some of the other flip-flops, right? We've got some other inputs that we're going to provide that will take care of this prohibited state. The other thing is, notice that we don't have, for this particular RS, we don't have a clock pulse, right? And so we're just looking at inputs and outputs, and you know, what we're going to see as we continue to move into our other flip-flops is we're going to see how that trigger, how that clock pulse really makes how it affects the action of this flip-flop, right? So right now we're looking at just the inputs and outputs. I'm either going to have an active low set, give me a 1 on Q, an active low reset, which is going to give me a 0 on Q, both ones, which is going to give me a hold, whatever state I had before, I'm just going to hold. And then the prohibited state of both being active, which I want to avoid. All right, so now let's take a look at a clocked RS flip-flop. And so really it's very similar to what we just saw. You can see we've added some more NAND gates. I've added another input, this clock pulse. You see I've got, you know, my set input, my reset input. I've got my clock feeding both of the NAND gates, and then the output of those NAND gates basically tying right back in where my inputs were with the previous flip-flop. The function is still the same in terms of active set and active reset. However, looking at the schematic, you'll notice that here we no longer have those circles on the inputs. So those state indicators, it no longer indicates that they're active low. Now it's indicating that it's active, you know, in absence of that state indicator, it's active high, right? And so that means that now a 1 on my set or reset will be what I'm looking for in terms of activating Q, right? So let's just take a look at what happens. We've got our, let's see, let's go to, so hold, you know, if we get a 0 on S, a 0 on R, meaning that neither of these inputs are active because they're both active high. There's no state indicator here indicating that they're active low, so they're both active high. If I get 0 on set and a 0 on reset, that's the same as we had before in terms of no input active, and therefore there's no change. It's a hold, right? Whatever Q was before, it's going to remain that way. If we look at a positive, you know, 1 on R, so a 0 on S, a 1 on R, that means I've got an active input on reset. The reset is going to send Q to a 0. So if I look at my output, I get Q as a 0, Q naught is a 1. Now notice that the conditions that have to occur, in order to get a 0 on Q, I've got to have a 1 on reset, a 0 on S or on set, and a positive clock pulse. Right. And so this clock pulse, when it goes from, I'm feeding that digital square wave, I'm feeding that signal in, right? So this clock is just going from high to low, whatever that square wave is set up to be, right? And so it goes from low to high, and when it goes low to high, that's going to be a positive clock pulse. I've got a active input on reset, and so this flip-flop goes to a 0 on Q and a 1 on Q naught. That clock pulse is going to continue whenever it goes from high to low. It's not going to be triggered when it goes the next square, when it goes from low to high. Once again, we get that leading edge. It goes from low to high. It's going to be triggered, and it's going to take a look at the inputs on S and R to see if a change needs to be made. If S and R are still the same, if 1 is still on R and S is still 0, well, it would continue to put a 0 on Q. If neither of those inputs are active at that point, so let's say they're both zeros, well, we'll continue to hold that 0 on Q. It's not going to change Q until it gets all of these variables met. I'm going to have something that's going to be a different output plus that positive clock pulse. So if we look at set, I get a 1 on S, and so that's active. I'm getting a 0 on R. So I've only got one active input, that's set. And then I get, that's going to give me a 1 on Q at my next clock pulse. And I think that's something to be aware of, is just because these inputs change, we still got to have this clock pulse. Otherwise, things aren't sequenced. And imagine that you're taking that same clock pulse and you're feeding multiple flip-flops, large number of flip-flops. And so now they are all shifting at the same time. They're all, fed, triggered off of that leading edge. And so as soon as that you get that low to high transition, then whatever those inputs are, you're going to get the output on Q. And it's going to hold it there until it gets another positive clock pulse plus an input that causes it to change. It tells it to change. Now, just like we saw before in terms of a prohibited state, a 1 on S and a 1 on R, both of these are active high. That would mean the S is saying, okay, set Q to a 1. R is saying set Q to or reset Q to a 0. And Q can't be both, right? Q can't be 1 and a 0. And so we just don't know what output we're going to get there. And so we avoid that status. We avoid both being high. So that is an RS flip-flop, but now it's a clocked RS flip-flop. We also have what we call this a D latch. And so this is, a D flip-flop. We've got our inputs are a little bit different, but they really act the same way in terms of PS is going to be a preset. Clear is a lot like the reset. And then we can have our data, our D, and then we've also got our clock. right? And so we've got those 4 inputs, and we've got our Q and our Q naught in terms of our outputs. If we look at preset and clear, both of those are what we're going to call asynchronous. Asynchronous meaning that it does not need a clock pulse in order to change or to impact the output. If I hit clear, it clears. It doesn't wait for a clock pulse to clear. If I hit preset, it's going to set Q to 1. It's not going to wait until I get a next clock pulse. Okay. So if we look at those 2 first, let's just take a look at set and reset. If I get preset, and once again, notice we've got our state indicator, right? Our state indicator on this input. What that tells us is what is the active status. What input do I need in order to activate this input? Here, since I've got this state indicator, this circle, that means that this is active low. Same thing is true with the clear. It's active low. So I'm looking for a 0 on preset or a 0 on clear, and that will automatically either set my Q to 1 for preset or set my Q to a 0 with clear. Right? So if we take a look at that, we see we've got our input preset is a 0, clear is a 1. We're not worried about clock. We're not worried about our D input, because this asynchronous active preset is going to automatically set Q to 1. Q naught then is always the opposite, which is going to be 0. Right? But look at the next set of inputs. Here I have preset with a 1 on preset. This is not active. I get a 0 on my clear. Clear is active low. And so now I have an active asynchronous input clear. That means immediately I'm going to get a 0 on Q. You see that 0 on Q. Thus, Q naught is the opposite, or 1. Notice that these asynchronous inputs, we didn't worry about the clock. It doesn't matter when it happens. Not looking for a leading edge to trigger it. These are asynchronous. The PS and clear are asynchronous inputs. Now, if we look at our other inputs, we have our prohibited status. If I get a 0 on preset and a 0 on clear, both of them would be active. That's not allowed. That once again gets us into the situation where we're going to have an output that we just can't rely upon. I mean, it may be a 1, it may be a 0. We just don't know. So we're going to stay away from having lows on both preset and clear. If we look at our D input, and so if I have a 1 on D, notice that is an active state on D. There's no bubble here. I have a 1 on D, and I have this positive clock pulse. This input now requires a clock pulse. So if I have a 1 and a positive clock pulse, then that's going to give me a 1 on Q. If I have a 0 on D, then that's going to give me a 0 on Q. Right. So as I've got, a clock pulse feeding into this, and I've got data that's coming into this, I'm going to be able to, once again, lock in or latch whatever this bit is, and then I can hold it so that I can perform some function with it later on. Right. And so this is what we're talking about with these flip-flops, these latches. It's just a matter of, holding a piece of data, a bit, a binary bit, holding it so that I can use it in typically a calculation or something at a later point. Keep in mind, we're really, really, really zoomed in, if you will, because in order for you to do something with data, you're going to have a lot of latches, because you're going to be dealing with large amounts of data. So we're really zoomed in, if you will. A JK flip-flop, you can see our number of inputs seem to be increasing. You see some common functions, some common inputs, the same Q naught output. We've got our preset, we've got our clear, we've got our clock, and we've got two inputs this time instead of the D latch, which had that D input and would basically latch it in place. Now I've got two. I've got the J and the K, and it's going to operate very close to what we've seen before in terms of all the different functions. I mean, if you look at our preset and our clear, both of them are asynchronous, meaning that they are not concerned about the clock pulse. As soon as they're active, they're going to change the status of Q. And you can see once again here for this JK flip-flop, preset and clear are both active low, right? So if I get a 0 on preset, a 1 on clear, not concerned about any of the other inputs. These inputs override JK, not worried about the clock. And so all of these other inputs really don't matter at that point. As when I get an active preset, that's going to cause my Q to be a 1, Q naught to be a 0. The opposite of that is if I get a high on preset and a low on clear. Clear is active low, active 0. Once again, it's asynchronous. It overrides the other inputs. And so therefore, immediately when I get the signal on clear, the active signal of 0, a low, I'm going to get a 0 on Q. Q naught's going to be the opposite. So a 0 on Q. Q naught is a 1. Just like before, the prohibited state is when I have an active preset and clear. We're going to avoid that. We're going to stay away from that output. That's not an output that we can be assured of what it will be. We go and we look at our synchronous inputs. Our synchronous inputs do not have a state indicator on J or a state indicator on K. Notice there is a state indicator here on the clock pulse here, right? And so it looks like we're talking about a clock that is going to be negative when it goes from a high to a low transition is what it. Well, we look at our J and K inputs, both are active high. If I get a 0 and a 0, that's neither are active, therefore no change, right? We're just going to hold what we got. We have a 0 on reset and a 1 on K. So 0 on J and a 1 on K. That 1 on K is going to act just like our R with our RS flip-flop. And so it's going to cause Q to be a 0. Q is a 0, Q naught to 1. If I get a 1 on J, right, so a 1 on J, a 0 on K, this is just like the S. J active is going to cause Q to be a 1. Q naught would be the opposite. And then if I get a 1 on both J and K, this is the thing that's a little bit different. Now I have to have a clock pulse, but if I get a 1 on J and a 1 on K, what will happen is it will toggle, meaning that it will change whatever state Q was to the other state, right? It can only be a 1 or a 0. And so if Q was a 1, then it's going to change Q from a 1 to a 0. If Q was a 0, and I've got an input of 1 on J and a 1 on K, then when I get the next clock pulse, it's going to toggle to the next state, right? And so that's something that's a little bit different with a JK flip-flop, is you get this option to toggle, right? You got your preset, your clear, your clock pulse, all of that's still the same. Your J is like your set that you were using before. Your K is like your reset. And then if you get active status on both J and K, then it will toggle. All right, when we're talking about these latches, you know, we say it's a fundamental digital storage device. We call it a latch because it likes to, you know, hold in place whatever the output is and lock it in. Right? We'll hold it in place. You know, RS and D flip-flops are example of latches. The reason they keep giving you that term, latches, is because they really like to throw that up in a quiz question, right? They will ask you, you know, a D flip-flop is also known as a latch, a D latch. And so that's something that, you know, there's a good chance you will see. I just heard multiple people talk about this notion of what's it called? It's a latch, right? Once again, we're zoomed in, right? We're really looking at some small components there because, you know, single flip-flop, so what we just looked at, it's going to hold 1 bit. We'd need several flip-flops together. You know, if we put 8 together, it could hold a data word, and we'd call it a register, right? You can take the register and you can begin to manipulate that data, and you can form counters, you know, things that will count up, count down. You can have arithmetic operations. So basically you could have it do math. You know, anything that you can do with that data, you want to do with that data, you could cause it to do that by taking some of these flip-flops, putting enough of them together so that you could hold in the data and then cause it to shift based on your input. You could have it, in other words, you could actually have it, and we would do this, you know, typically in a digital class, is you'd build a register. And so you would take the ICs that contain these flip-flops and you would wire them, and then you would connect to appropriate inputs, have a clock pulse so that you could cause it to shift and go from, you know, 10, 9, 8, count down, count up, you know, and do other functions as well. We call this flip-flop. It's the basic building block of sequential logic. Sequential logic, just because we're sequencing all of this data. Now, one of the things that when we keep talking about data and we keep thinking about triggering these flip-flops, the way we trigger these flip-flops is important. If we go back to some of the original slides that we looked at, we had a signal that looked like this square wave, right? It was very vertical when it went from a low to a high and back down to a low. We got these sharp edges, and what that allowed us to do is use that square wave to time up to trigger these latches and make sure that they were sequenced right. They were all moving at the right time. If I tried to do that with a wave that looks like this, a sine wave, and I said, well, I want it to trigger at somewhere between 0 and 5 volts, which really that's what's happening is it's triggering here when it goes from 0 to 5 volts, and it causes that immediate trigger. Well, 0 to 5 volts, you can see how it takes longer to get there, and the trigger is not going to be as precise. Some may trigger slightly before others. And you think about this wave as it's continuing, could be compounded over every cycle of this wave. And so what we really need to have is a steady square wave, really sharp square wave, as opposed to a sine wave when we're using these flip-flops and when we're working with working in digital, right, in this digital data. And so we've got this, what we call a Schmidt trigger. And basically this Schmidt trigger is going to trigger at a certain voltage, and it's going to cut it off, right? And so we get this very, off, on, off, on, back and forth, a really sharp square wave that's really works well for us when we're dealing with these flip-flops. We're avoiding this sine wave input, working toward this square wave. This is what we need. And so Schmidt trigger does exactly that. It's going to square up the waveform for us. Now, we also could have to time up some of these signals, if you will. If simply just because of the distance, you may need to have some delays built in, and so you could have what are these devices, these delay lines, either a single tap or a multi-tap. And what I'll say about these really is look at the units you're working in, right? I mean, 3 nanoseconds, right? So we're really talking about small increments of time. This would be a single tap, meaning that you're basically delaying what's coming down this line by 0.5 nanoseconds. Here, this multi-tap, you're delaying what's coming in by any of these options that you might need. And you're really getting into some really tight tolerances, if you will. It's probably not the best way to say it, but you're not talking about a lot of time there, and it just goes to show how precious and how important the time is in the sequencing, how important the sequencing is when you're dealing with these, with this digital data. All right, let's see if we can come up with some of this information that we just took a look at. if we're looking at in the figure shown, which is the positive edge trigger?
A.
A, okay. How do you know it's positive edge?
That question is not part of the review questions.
Well, I mean, really when we're looking at that positive edge, it's going from a low to a high, right? So it's going low to a high. It's going from a 0 to a 1. So if that's the positive edge, what's the negative edge?
C.
C, okay. All right. In the figure shown, which is the positive trigger?
B.
Yeah, I'm not a big fan of the way that's worded, but yes, it should be B. And then what's the negative trigger?
D.
Got to be D, right? Very good, very good. All right. What's the purpose of that Schmidt trigger? That was one of those last slides that we saw, and really that Schmidt trigger is all about the waveform that it provides, right? That square wave waveform that we're gonna get out, right? A flip-flop is also known as a
Latch.
latch. Yep. And then in the figure below, if S is low and R is high, what is the mode of operation and the state of Q?
It'll be low.
Okay, so if S is low and R is high, which one of these input is going to be active? Is it going to be S or R?
Could you repeat that?
Yeah, if S is low, so I've got a 0 here on S, and R is high, so I've got a 1 on R, right? Let me do this. So if I've got a 0 on S and a 1 on R, which one of those inputs is active? S or R?
I'm gonna go with R.
Okay. Why would you go with R? Or maybe I should ask it this way. How do we know which one's active?
Well, I thought you had said whenever you have voltage on the line, you would have it would be active.
But shouldn't it be reversed?
Why would it be reversed?
There's no clock on it. There's no clock on it, so it can't be reversed.
Okay, so it's not so much a clock issue. Why would it be reversed?
Because the little circle.
Don't forget these little state indicators. What they are going to tell us is if this input is active low, if it's got a circle here, it's going to be active low. No circle, it's going to be active high. Okay. And so when we take a look at these inputs, we got to know if this is going to be active low or high, because that's going to tell me whether it's going to be in set mode or reset. Here, since I've got this state indicator on S, that tells me that it's active low. I've also got one on R. It's active low. And so the active input is here, that 0 on S. So that means it's going to be in set mode, right? This is set. And so if it's in set mode, what does that mean about Q?
It's going to be low.
Q's going to be high.
So since there's only two states that it can be, and I heard a low and a high, we're right. Yes. So if I set, Q is going to be a 1. If I reset, Q is going to be a 0. All right. What the trick is, I've got to figure out which input is high, or I'm sorry, which input is active. And it's always based on the state indicators. If I've got a state indicator that has, I've got these state indicators on the input, then that means it's active low. If I don't have that, if I've just got a line that goes straight in, no bubble, then that means it would be active high, right? Set is always going to be a 1 on Q. Reset is going to be a 0 on Q. So in this situation, what's Q not?
A 0.
It's got to be a 0, right? Q naught is just the opposite of Q, and so that means that it's a 0. Yep. So there we go. All right. Figure shown below, when will the clock pulse cause a change in the mode of operation? So before we even answer the question, look at my S and my R. Are they going to be active high or active low?
Active low.
Okay, remember, how do I know? I'm looking to see here if I've got a state indicator or not. If I've got this state indicator, it means it's active low. If I don't have a state indicator, see no bubble here, no circle. If I don't have a state indicator, that means it's active high. You see the difference between that, oops, and this? Here, state indicator, that circle, active low. Here, no circle, active high. That means I'm looking for a 1 to activate S or a 1 to activate R, versus here, I was looking for a 0 because it's active low, or a 0. So we've got this RS flip-flop, and we're looking to see when will the clock pulse. And here's my signal. This is what is being fed into this flip-flop. The figure shown above, if S is low, so let's just do this just to, so we can keep it straight. S is low, so 0. R is high, so 1. So which input is active, S or R?
Little boy got kidnapped.
Yes.
All right, so no bubble, no state indicator, nothing indicating that it would be active low. So I'm looking for a high. So does this is a low, I'm looking for a high. This is a high, I'm looking for a high, right? And so this R is active, S is not. You guys see why?
Because of the bubble not being there?
Yeah. Since we don't have the bubble there, there's no bubble. That means it's active high. This is a low, 0 is a low, so it's not active. No bubble here. It's active high. It's active 1. So I get a 1 on reset, and so it's active. Right? I'm looking for that bubble. And if I have a bubble, then I know that I'm looking for zeros on that input for it to be active. If there's no bubble, then I'm looking for 1s on that input for it to be active. Right? And then it's just a matter of saying, okay, now where do I have the appropriate input? If I'm looking for a 1 on S and I got a 0, well, it's not active. I'm looking for a 1 on R because there's no bubble. and I got a 1. So, okay, this one's active. So I'm looking to reset this RS flip-flop. And the question is, what will be the mode of operation after the next clock pulse? And so, well, that was the second question. I was going to say that doesn't make any sense with that A, B, C, and D. The first question is, in the figure shown, when will the clock pulse cause a change in mode of operation? So where are we triggering? What do you think? Let me erase some of these. Okay. All right. So what it's saying here is this is going to be positively triggered, but since there is nothing indicating, there's no, looks like an arrow here indicating that it would be on the edge trigger, then it's saying that we're going to trigger on the level, right? So on this B, we go back and you won't see a clock. I'll show you the difference when we get our next clock pulse. And then going back to the second question, if I'm feeding a active input into R is reset. Reset meaning that I'm going to change this Q to a 0, right? So reset Q equals 0. Q naught is going to equal a 1. I think we got one more so we can. All right, so this is our D-latch. We had a couple asynchronous inputs. What are our asynchronous inputs? Which ones are asynchronous? Remember, asynchronous meant that it was not timed with the clock. It takes precedence over the other inputs, and as soon as it is found active, it will change the state of Q.
I'm guessing PS.
Yep. So preset is 1, and what's the other one?
The CLR.
The clear. Exactly.
Clear.
Preset and clear are both asynchronous, meaning that they do not need a clock pulse. You know, as soon as you hit clear, it's cleared. As soon as you hit preset, Q is a 1, right? Now, notice those two inputs. Tell me in terms of preset, PS, is this input based on this state indicator, based on this bubble, will it be active low or active high? Is it looking for a 0 or a 1 here to be active?
That's where I think that's a 0.
Yes.
0.
Yes. Yes. Exactly. Now we're getting it. Yes. So when we see this state indicator, this bubble, this looks like a little 0. That means it's looking for a 0. It's looking for a low before this will be active. How about on the clear? We're looking for a 0 or a 1 for it to be active.
The same.
Same, right? It's a 0. It has that same state indicator. And so if I get a 0 on my preset, that's going to be, it's the same as set. It's asynchronous. It's going to set my Q to 1, right? Preset, if it's active, I get a 1. Clear, if it's active, I get a 0 on Q, right? So those are both active. Low, I'm looking for 0s. So those are my two asynchronous input. I don't know what it's talking about. PC, CLR is what it should be. In terms of the trigger, see when we just had this input and nothing here. See how we've got this arrow? That's what's indicating that it is triggered on positive edge, right? If we look at what we had here with the clock, see how we don't have anything there? And since there's nothing to indicate that it would be negative, it's just going to be this positive level. Typically what we're going to see is going to be something that looks like this, right? We're going to have that positive edge so that we can, trigger, and the timing be even closer together. And then, what is the asynchronous input? Well, that just means that those inputs are going to be used outside of the clock pulse. It doesn't have to have a clock pulse in order to impact the output. Okay. Wait a minute, let me go back. We got one more. We'll practice one more time. So here we have our JK flip-flop. We've got, once again, a couple asynchronous inputs. We've got JK and we've got our clock. Let's see. In the figure shown, if J is high and K is high, right, what will be the mode of the operation of the next clock pulse? And so if we take a look at, it's not what I want. All right, you guys see that?
Yes.
All right. So it's saying if J is high and K is high, what will be the mode of operation of the next clock pulse? And so we're looking at these two inputs, J and K. What can you tell me about those two inputs? Is J active high or low? I'm looking here to see if I've got a high. There's no bubble, so I'm looking for a 1. What about K?
High, no bubble.
No bubble, high. You guys got it. Absolutely. So I'm looking for highs. And what it's saying is I'm getting a high on both J and K. Right? Now, there was something that was unique about the JK flip-flop that was a little bit different than the other flip-flops. Most of the time when we had this situation where both were high, we said, well, that can't be because they're both active. If they're both active high and they're the same, that's going to cause an issue. But here, it actually is able to do something with both of those being high. What does it do? If J is high, K is high, both are active, what's my output going to do?
Opposite.
It's going to be the opposite. It's going to toggle. Very good. Very good. Yeah. And so it's going to change. If it was a 1 before, it's going to change to a 0. If it was a 0 before, it's going to change to a 1. So absolutely, it's going to toggle. In the figure, what type of triggering is used? Triggering, we're talking about our clock. It's asking about our clock. You can see that we've got this arrow again. And so that indicates that we've got edge triggering, but we've got this bubble. What do you think that means? Knowing what we know about that bubble, what could that mean? First, let me ask you like this: is it level triggered or edge triggered?
Edge triggered.
Edge triggered. All right, so edge triggered.
Triangle.
And then the other key piece of that is, since we've got this bubble, instead of it being the positive edge where it is that leading edge that goes from 0 to high, this is going to indicate that it's that negative edge triggering. And so it's the lagging edge. It's when it goes from high to low, right? And so it's just, moving the edge, if you will. In the figure above, if J is high and K is low, what will be the mode of operation at the next clock pulse? So if J is high, K is low, which one of those are going to be active, J or K? Got a high on J, a low on K. Remember, what does J need to be active? No bubble, so it needs a high. K, no bubble, so it needs a high. So if I've got a high on J and a low on K, which one of these is active? J or K?
J.
J, right? So if J is active, the next clock pulse, what's going to happen to Q? We said J was like the set, right? And so Q is going to be a
high, a 1.
Yeah, exactly. Very good. Good job. It's easy to get lost in those things. But the good news is you're not going to have to go in and take an entire register and try to calculate and figure out the trace signals through it, digital logic through an entire register. All right. Pull this up.
The following program is brought to you by Element 14, the electronics community where you can connect and collaborate with top engineers from around the world. Join now at element14.com/presents.
Hi, and welcome back to the Learning Circuit. Today, we're going to learn about flip-flops, but not the kind you put on your feet. Nope, we're talking about logic devices packaged into ICs. Our last lesson was about multiplexers, demultiplexers, encoders, and decoders, combinational logic devices where the output is dependent only on the current state of its inputs. Flip-flops, or latches, are sequential logic devices which have a form of memory built in. This means they can use not only the data from their current inputs, but also previous data from their inputs and/or outputs. Flip-flops are bistable devices, meaning their inputs and outputs can be at one of two states, a logic level 0 or a logic level 1. Flip-flops can be made using logic gates, and we'll be using them in our examples. If you're not familiar with logic gates, I highly recommend you go back and watch that episode of the Learning Circuit first so you can follow along more easily. We'll start with one of the most basic sequential logic circuits, the SR flip-flop. An SR flip-flop or SR latch has two inputs, one that sets the device and one that resets the device, usually labeled S and R. Its output Q will be at either logic level 1 or 0, depending on the state of its inputs. The second output, not Q, or sometimes also called bar Q or Q bar, is typically the inverse of output Q. So if Q is 1, not Q is 0. If Q is 0, not Q is 1. If you remember from our logic gates episode, a circle on a symbol indicates that it is the inverse of the main symbol. Looking at this logic diagram of a flip-flop, you can see the circle on output not Q, indicating that it is the inverse of Q. SR flip-flops can be active high or active low. In an active high circuit, the inputs are normally low, a logic level 0, and go to logic level 1, high, when active. An active low circuit is the opposite, where the inputs are normally high at logic level 1 and go low when active. This SR flip-flop made of NOR gates is active high. Remember that the output of a NOR gate is high only if both inputs are low, otherwise the output is low. One input of each NOR gate is connected to set or reset. Notice how the second input of each gate is connected to the output of the other gate. This strange connection is essential to the function of a flip-flop. Since this SR latch is active high, the inputs are connected to ground, normally low. When the set input is active and goes high, it sets the latch and output Q goes high. If the set input goes low, output Q doesn't change. It stays high. It is latched. The reset input must be active, going high, for the latch to be reset, returning output Q to low, its normal state. So an active set input sets the latch with output Q going high, and output Q will not change until the reset input is active, resetting the output back to its normal low. If set and reset are simultaneously active, going high at the same time, an invalid state is triggered. But I'll get into that more a little later. Just know that it's bad. First, let's take a look at the other type of SR latch, an active low flip-flop, this time made of two NAND gates. Remember that the output of a NAND gate is high, unless both inputs are high, making the output low. Notice the inputs on this flip-flop are set bar and reset bar. This tells us they are active low, meaning the inputs are normally high. With this flip-flop, output Q is latched high when the set input is active, going low. Again, output Q remains latched high when set returns to its normal high. When the reset input is active, going low, output Q is reset back to low. So whenever set goes low, output Q goes high and latches there, until reset goes low, resetting the flip-flop. With both types of latches, the set input being active triggers the Q output to go high, no matter if the input is active low or active high. And the reset input being active resets output Q back to low. SR latches can also be gated. I'll show you what I mean. To make an SR latch gated, two input AND gates are added, one each to the set and reset inputs. The second inputs to each AND gate go to a single enable input. Per the rules of AND gates, the enable input must be active for the set and reset inputs to be able to affect the outputs. If the enable pin is off, S and R can change, but they won't affect the outputs. As long as the enable pin is active, signals at set and reset can trigger the outputs. By understanding how gated SR latches work, we can begin to understand the two main types of flip-flops, D-type and JK. D-type and JK flip-flops have an additional input pin for a clock signal, usually labeled clock or clock pulse. This pin enables the flip-flop to be triggered according to a clock signal. The outputs flip-flop between high and low with every active clock edge. Active high flip-flops are triggered at the rising or positive edge of a clock pulse. Active low flip-flops are triggered at the falling or negative edge of a clock pulse. You'll also often find a data input. The data pin is an additional input that can be set high or low. The clock signal acts as an enable pin for the data input. If output Q is low and then the data signal goes high, on the next clock pulse, the data signal gets through and makes output Q go high. If the data signal goes low, output Q won't go low until the next clock pulse. So the clock acts like sort of a valve for the data signal. This data signal is considered to be synchronous, as it changes the output in time with the clock signal. In these flip-flops, the set and reset inputs are asynchronous. They have priority over the clock signal and can affect the outputs at any time. While the data signal has to wait for the next clock pulse before it affects the output, as soon as set goes active high, it makes the output go high. And anytime reset goes active high, it resets the output back to low. With D-type flip-flops that have set and reset, there's a potential problem that can occur. We know that set latches output Q high, and reset resets it back to low. But if both set and reset go active at the same time, the flip-flop enters an invalid state. Inputs Q and not Q, which should ideally be inverse, can become both high or both low. This causes the flip-flop to lose control of the outputs and their future states become unpredictable. Long story short, it's bad. But this is where JK flip-flops come in. Let's look back to our original model of a gated SR latch. In a JK flip-flop, the two 2-input AND gates are swapped out for two 3-input NAND gates. Having the third inputs of each NAND gate connected to the opposing outputs eliminates the invalid state. Inputs J and K still behave like set and reset, setting Q and then resetting Q. But if both J and K go active high, the outputs simply toggle. Boom, no invalid state. Problem solved. These circuits are considered sequential logic because the logic happens in a certain sequence. Makes sense, right? If you start looking for flip-flop ICs, you may come across some inputs that I haven't mentioned, like preset and clear. Now your homework is to figure out what they do and how they work in the sequence. Report back and post your answers in the comments on the Element 14 community on element14.com/the learning circuit. Happy learning!
So one thing about that video is you can see when you start getting into the gates and really looking at the gates of some of the flip-flops and the way those combinational circuits are tied together, it can get complex and it can be a challenge. So like I said, luckily we're not going to have to trace signals through one of those gates. You're just going to be called upon to take a look at the schematic symbol and for any given set of inputs, be able to determine what Q and Q naught would be. All right, so looks like we're at 1/2 the hour. Let's take a break and see you guys come back at 1/4 till. All right.
They came with helicopters, the people that are trying to.
All right, so let's take a look at data communications. The good news is we've gone about as deep as we're going to go in terms of gates and flip-flops, and so now let's just kind of step back and kind of shift a little bit, still related to the same topic, but just change our focus just a little bit. And so let's talk a little bit about data communications, and specifically let's take a look at characteristics of data communication. And we'll just start off talking about communication in general, and then look at this notion of a DS0, a T1, a T3. Probably things that you guys are very familiar with and very comfortable with anyway, right? And so as we're thinking about data communication and how we communicate, how we share information, data communication is something that has taken place for ever since there were people, right? Ever since we needed to communicate, we've come up with ways to communicate with one another. We've come up with ways to get each other to understand whatever we're trying to understand. And there's some key elements that always are always there. Whether we're looking at data communications today and some of digital and some of the communication lines, or if we're going further back, and we're looking at if you keep walking back, and there's a video that I'm thinking about. There was a pretty good, the guy has a pretty good joke, but he keeps changing the communication method. I have to see if I can find that joke. But if you go backwards and you start thinking about how we communicate, today, obviously with cell phones, communication is so easy. The methods of communication, whether it be voice or it be text or whatever, and then you go back before that, right? You can keep rolling the years back and think about how you would communicate. But there's always those key elements, always those key components that are there. Whether you go back to old
Pagers, a pager.
pagers. If you continue to go back even further to old style rotary phones, if you go back to party lines, heck, if you go back to smoke signals, there's always some key elements of communication. Any idea what some of those key elements might be? If we're going to communicate with one another, typically there's always a sender, right? There's a receiver. There's somebody that is going to receive what I'm sending. There's some message I want to share, right? There's the message that's going to be sent. There's some medium, whether it be, over.
Are you showing a different slide?
Not yet.
Okay,
Not yet. But we're going to see it here in a second. Hopefully, you guys are still seeing the slide that says data communications.
Yes. Okay, making sure.
Yeah. And so you've got sender, receiver. You got medium. You got the message, and then you've got one other thing. Typically, you've got some set of rules, right? You've got some protocols that are in place, right? So let's just take a look at what that is. A message. You want to communicate something. There's something that you want to share, and so you say, okay, now how do I communicate this to the other user, the sender, right? So that's the person that's starting the communication, the location of the origin of communication. right? It could be, nowadays a workstation, a server, a telephone handset. It could be, the fire. If you keep rolling back to smoke signals, the receiver, somebody's got to receive it. Who's on the other end? Somebody's got to observe it. The transmission medium, how does that medium get from one place to the other? Is it over some type of cable? Is it radio waves? Is it in other words, wireless? Is it fiber? What is it? And then finally, you got that set of rules. Those rules that are in place so that you can make some sense of how the data should flow and how to make some sense of the data, right? I mean, you can think about those 5 elements. They ring true, whether it's networking, whether it's like I said, a conversation that's being had between 2 people face to face, and you got a message, you got a receiver, a sender, you got airwaves, and then you got a protocol. That conversation, typically you got a language, a list of rules that you have for language, so we understand that those sounds mean certain things. And so you've always got kind of these 5 elements that come into play. Obviously, we're going to focus on the networking piece of it and digital, data communications that's taking place over our networks. Now, we start thinking about communicating over these networks, and you kind of roll the clock back just a little bit. You start hearing about this DS0, this line that can carry a single conversation, and you come up with the standard rate, this 64K, what's required to carry, if you will, that single conversation, and that becomes kind of the baseline. The DS0 is the baseline that we're going to kind of use as we continue to move forward, and we look at some of these larger bandwidths that we can use to carry more data. But you can typically roll it back and talk about 64K and how many channels of those DSOs you can have, right? If we look at a T1, you got 24 DSOs. So you got, if each one of those DSOs is 64K, then that means I've got 24 64K channels that I could use for this T1 line. And then if you look at a 28 DS1s or T1s are then multiplexed into a DS3 or a T3, right? So you got, if you had 24 64 channels in a T1 or a DS1, well, you got 28 of those in a DS3 or a T3. And so, the thing there is you can do the math and do the calculations and figure out the bandwidth of each of those. But it becomes very easy to see how much larger a T3 is versus a T1. 28 times, you're talking about a lot more throughput, a lot more data, a lot more, whether it be data or voice, can be carried over that T3 line versus the T1 versus the original 64K channel that we're talking about. Here's some of your throughput. So a T1, 24 channels, 24 of those 64K channels, 1.54 megabytes. You see that you can utilize compression to double that, to increase that. And then if you see with moving from a T1 to a T3, so now you got your T3, which was 28 of the T1. So now you're at, 45 meg offered broadband connection consisting of 672 individual 64K channels. And that 672 would be the 24 the T1 and the 28 T1s that make up a T3. And so that's how you get the 672 individual 64K channels. You can see what it's saying here in terms of T3. Usually you're using those T3 lines. You're talking about a lot of throughput, a lot of bandwidth. It mentions research centers, IP telephony, telemedicine, data centers, video conferencing. You're talking about a lot of throughput that you need when you're paying for a T3. Hold on 1 second. I want to see if I can. We'll go back to our class. I'm not sure if this is in our class. If it's not, I'm going to pull it up so you can see it. So I'm going to share this video. Obviously, when we're talking about data communications, we're moving toward networking and looking at data traveling over the network. We've just coming out of the conversation about ones and zeros. We've been working through digital, and now we're talking about moving some of that data. And so I want to share this. This is an old video. And it's not necessarily it's I think it's a good representation, and it's a light look at networking and some of the devices on the network. Not a deep dive by any means. This is not a indication of what routers and switches and different devices do. It's just kind of a interesting and almost comical way of looking at some of this. And I figure with some of the challenging material we've gone through in the past 2 days, it would be a welcome light moment in the class. So I'm going to show you this, and then we'll talk about data traveling after this video. Let's see.
For the first time in history, people and machinery are working together, realizing a dream. A uniting force that knows no geographical boundaries without regard to race, creed, or color. A new era where communication truly brings people together. This is the dawn of the net. Want to know how it works? Click here to begin your journey into the net. Now, exactly what happened when you clicked on that link? You started a flow of information. This information travels down into your own personal mailroom, where Mr. IP packages it, labels it, and sends it on its way. Each packet is limited in its size. The mailroom must decide how to divide the information and how to package it. Now, the package needs a label containing important information, such as sender's address, receiver's address, and the type of packet it is. Because this particular packet is going out onto the internet, it also gets an address for the proxy server, which has a special function, as we'll see later. The packet is now launched onto your local area network, or LAN. This network is used to connect all the local computers, routers, printers, etc. for information exchange within the physical walls of the building. The LAN is a pretty uncontrolled place, and unfortunately, accidents can happen. The highway of the LAN is packed with all types of information. These are IP packets, Novell packets, Apple Talk packets. They're going against traffic, as usual. The local router reads the address and, if necessary, lifts the packet onto another network. The router, a symbol of control in a seemingly disorganized world.
Whoops, sorry about that. Let's go with this one here, this one here. This moves here, this one goes here. I don't like this one. Let's go with this one. Let's go here. A little bit left, let's go with this one here. Another channel here. Let's put that one here. Another one there. Let's put that one here.
There he is, systematic, uncaring, methodical, conservative, and sometimes not quite up to speed.
Sorry.
But at least he is exact, for the most part.
That one goes there, that one goes there, that one goes there, that one goes there, and this one goes there. Well, another one goes there, that goes there. He's behind him, let's go there, that goes there, he goes there, let's put that one there.
As the packets leave the router, they make their way into the corporate intranet and head for the router switch. A bit more efficient than the router switch plays fast and loose with IP packets, deftly routing them along their way. A digital pinball wizard, if you will.
Here we go. Here comes another one. And it's another. Watch this, Mom. Here goes. Whoop, we're on the back. Hey, in there, in there, in there. Over the left, over the right, over the left, over the right. You got it. Here it comes. Right on. He shoots. He scores. It's going. Hey, wait. Here, watch out. Here comes another one. Oh, here we go. And it's gone. It's gone.
As packets arrive at their destination, they're picked up by the network interface, ready to be sent to the next level. In this case, the proxy. The proxy is used by many companies as sort of a middleman in order to lessen the load on their internet connection, and for security reasons as well. As you can see, the packets are all of various sizes, depending upon their content. The proxy opens the packet and looks for the web address or URL. Depending upon whether the address is acceptable, the packet is sent on to the internet. There are, however, some addresses which do not meet with the approval of the proxy, that is to say, corporate or management guidelines. These are summarily dealt with. We'll have none of that. For those who make it, it's on the road again. Next up, the firewall. The corporate firewall serves two purposes. It prevents some rather nasty things from the internet from coming into the intranet, and it can also prevent sensitive corporate information from being sent out onto the internet. Once through the firewall, a router picks up the packet and places it onto a much narrower road, or bandwidth, as we say. Obviously, the road is not broad enough to take them all. Now you might wonder what happens to all those packets which don't make it along the way. Well, when Mr. IP doesn't receive an acknowledgement that a packet has been received in due time, he simply sends a replacement packet. We are now ready to enter the world of the Internet. A spider web of interconnected networks which span our entire globe. Here, routers and switches establish links between networks. Now, the net is an entirely different environment than you'll find within the protected walls of your LAN. Out here, it's the Wild West. Plenty of space, plenty of opportunities, plenty of things to explore and places to go. Thanks to very little control and regulation, new ideas find fertile soil to push the envelope of their possibilities. But because of this freedom, certain dangers also lurk. You'll never know when you'll meet the dreaded ping of death. A special version of a normal request ping, which some idiot thought up to mess up unsuspecting hosts. The paths our packets take may be via satellite, telephone lines, wireless, or even transoceanic cable. They don't always take the fastest or shortest routes possible, but they will get there. Eventually. Maybe that's why it's sometimes called the worldwide wait. But when everything is working smoothly, you can circumvent the globe 5 times over at the drop of a hat. Literally. And all for the cost of a local call or less. Near the end of our destination, we'll find another firewall. Depending upon your perspective as a data packet, the firewall could be a bastion of security or a dreaded adversary. It all depends on which side you're on and what your intentions are. The firewall is designed to let in only those packets that meet its criteria. This firewall is operating on ports 80 and 25. All attempts to enter through other ports are closed for business. Port 25 is used for mail packets, while Port 80 is the entrance for packets from the Internet to the web server. Inside the firewall, packets are screened more thoroughly. Some packets make it easily through customs, while others look just a bit dubious. Now, the firewall officer is not easily fooled, such as when this ping of death packet tries to disguise itself as a normal ping packet.
It's okay, Gorm. It's okay. No problem. Have a nice day. Be out of here. Bye.
For those packets lucky enough to make it this far, the journey is almost over. It's just a line up on the interface to be taken up into the web server. Nowadays, a web server can run on many things, from a mainframe to a webcam to the computer on your desk. Or why not your refrigerator? With a proper setup, you can find out if you have the makings for chicken cacciatore or if you have to go shopping. Remember, this is the dawn of the net. Almost anything's possible. One by one, the packets are received, opened, and unpacked. The information they contain, that is, your request for information, is sent on to the web server application. The packet itself is recycled, ready to be used again, and filled with your requested information. Addressed and sent out on its way back to you. Back past the firewall, routers, and on through to the internet. Back through your corporate firewall. And onto your interface. Ready to supply your web browser with the information you requested. That is, this film. Pleased with their efforts and trusting in a better world, our trusty data packets ride off blissfully into the sunset of another day, knowing fully they have served their masters well. Now, isn't that a happy ending?
So obviously that's not exactly how things happen, but I do like that video, and it's a old video. I think it was made back in around 2011 or so, probably even before that. But if you think about the elements of communication that we were talking about, sender, receiver, there was a whole lot of time in that process where you're worrying with the address of either the sender or the receiver. That you spend a lot of time, and a lot of that packet that's going over the net is all about addressing information. Then you also have the message, what was requested in the very beginning, what's contained in the packet. You've got the media, and we saw it traveling on what looked like different types of media as it went from the LAN to the internet to the local network. You saw what looked like a change in medium, and then the fact that you had all of the rules along the way, right? You've got the different protocols. I mean, everything from the port numbers at the firewall, to understanding how the addressing is going to be done, the whole encapsulation, decapsulation process. And when we get a little bit further into networking, we will look at the OSI model, and we'll talk about how all of that takes place. But there's rules that are set into place, and for all of those different packets that are traveling, and all those different devices that are communicating. And so, when we talk about data communications, those 5 elements of data communication, they exist. They are there, all the time. Like I said, when we're communicating, day to day, or when we're communicating on a network. All right, so let me get back to session 9.
Hi, my name is Dave Andrews. Today I'm going to talk to you about T1 lines. Now the question I'm going to answer is, what is a T1 line? A T1 line is a system that's delivered to a company and maintained by a company by the telephone service that that company uses. A T1 allows you to basically connect multiple buildings together with a very fast network connection, or you can connect to the internet using a T1 and get a very fast internet connection. Now, the way it does this is actually through a combination of telephone lines. If you have, let's say you have 24 telephone lines, you have a 24-port T1. You can take 16 of those lines and you can dedicate those 16 to be used primarily for internet traffic. Each one of these lines is basically a back and forth telephone line like you get to your house. But you can have 16 separate lines devoted to internet and the rest of those lines devoted to telephones. That way you can have 8 lines for your company. You can do it to where you have 20 lines devoted to the internet and 4 lines devoted for telephone. The more lines you devote to an internet connection, the faster your internet connection will be. If you only use 2 of them, it'll be a slow internet as opposed to 20 of them using a fast internet. Let me show you a quick picture here of a T1. Now, down here at the very bottom, this is what's interesting here. The T1 line comes in from the telephone company and it then connects to a T1 router of some type. Now, it's that router that does the breaking up and controlling of what each of the lines that the T1 uses will be. Now, that has to be programmed into some sort of external device from the T1 because the telephone company is only providing you the lines. They don't really care what you use them for. So it's important to note on a T1 that it's basically a combination of telephone lines from the telephone company that can be used as either data transmission for internet connections or for telephone transmissions for voice, just like we're used to using.
So I had a question. So the fiber's pretty much getting rid of all the T1 circuits. Are they?
Say that again.
Like the fiber that AT&T is installing, are they getting rid of, pretty much becoming obsolete?
Yeah, what it seems like to me, and granted, I'm not on the ground doing it, but I know where they're putting fiber in around here, they're replacing, all of that existing lines that are in place. So there may be some cases where they put in parallel fiber and just an additional fiber, but around here, I know they're replacing a bunch. Yeah.
Okay.
I don't think, because they got a bunch of equipment that, like, let's say the fire department's using, all the city of Dallas, that they're not upgrading none of that stuff because all their equipment is not it's obsolete. I guess they got old equipment. So that means the city of Dallas would have to change all the equipment. So that's why they still have the copper, the T1s.
That's a great point. And the thing about fiber, if you put it in parallel, now you have additional throughput, and you had what you had before, right? And so the places where they're replacing fiber, copper with fiber around here, I'm not sure how that decision was made, but I know that's taking place in a couple of different places around here. But yeah, I could see that. I mean, you'd have to go in, and end users would have to look at buying additional equipment, upgrading equipment so that they could take advantage of the fiber. Good point. Looks like that video may not play. Okay. I'll have to see if I can find a replacement for that trunking video. All right. So it looks like what we've got coming up, we're going to start getting closer and closer to computers. And we're going to look at, and there was a couple questions early on in the course about operating systems and computers. And so we're going to look at basic computers and operating systems. I don't want to split that up. So we're going to do that on Monday of next week. And so with that being said, let me back up.
I know.
All right. So just take a few minutes, and since we are going to really get through session 9, the material in session 9 with some time left before we do the same thing we did last time. I'm going to give you a little bit of time. I do want to just maybe take a few minutes to review here. And so let's just work through a couple problems, kind of go back. You know, when I get to a question that on material we haven't covered yet, we'll just skip over it. But just a couple problems. I don't think we got this far in last time. We went through a review, a basic review. And so let's see if we can solve some of these problems. So given 30 volts or voltage applied, we've got 5 ohms, 10 ohms, and 20 ohms. What's the voltage across R2?
30 volts.
30 volts. How'd you get 30 volts so quick?
Because it's parallel.
Absolutely, right? Absolutely. Yeah, nice catch. Most definitely. It's parallel, so it's 30 volts across all 3 of those resistors, R1, R2, and R3. You know, it's natural tendency for us to dive in and start doing calculations. Yeah, good job. 30 volts. Okay. All right. This is a little tricky. Not sure if you remember some of the values here. Given 10 volts, what is VP? What does that mean?
Voltage peak.
Voltage peak. Yeah, absolutely. Voltage peak. Given 10 volts peak, what is the voltage RMS value? Remember, RMS was really what our meter is going to read, that root mean square. What was that?
7.07.
7.07. Absolutely. Absolutely. The formula was, if we would multiply, it was basically 70.7, or let me say that again, 0.0707 times peak. So 70.7% is what it works out to be. Absolutely. Very good. There we go. Great job. What is the voltage between points A and B?
15 volts.
15 volts, right? Looks like all those voltage supplies are pointed in the same direction. They're all series aiding, right? So yeah, 15 volts. What device opposes changes in voltage?
Resistors.
Okay, now resistors oppose current, right? They oppose current. You know, they oppose current flow at all times. If it's steady, they still oppose current, right? So it wasn't resistors.
Capacitors.
Capacitors. Remember those capacitors, they charge up to a certain voltage and they hold that voltage. And then whenever the voltage change, they will actually discharge to try to maintain the same voltage. So absolutely. What is power total for the circuit shown? How are we going to solve this? You know, there's two ways. We talked about that power formula that was more difficult to remember, that just had voltage and resistance. You could use that if you remembered it. Voltage squared divided by R. However, you don't have to use that. You can always go back to power formula. Power is equal to current times voltage, and use Ohm's law, right? And so the first thing I would have to do is figure out what is my current. I know my total resistance is 25 ohms, right? Current is equal to voltage divided by resistance. So 12 divided by 25 is going to give me what's 12 divided by 25? It's got to be right at 0.5. 0.48. So just about half. And then I multiply that. That's my current, 480 milliamps, or 0.48 times 12. About half of 12 is what I'm going to get, right? And so if I look at my answers, the actual correct answer is 5.7. It's B, 5.7 watts. Absolutely. Yeah, a couple steps I have to take there, but I can always use power is equal to current times voltage and Ohm's law to figure out what my current is. Those two steps will never do you wrong, right? So there we have power total. I had my, this is the current, or voltage squared divided by R. That will work. Or calculate your total resistance, 25 ohms. We use Ohm's law to figure out our current of 0.48 amps. And then we use the power formula, current times voltage, which is going to give me 5.76 watts. Yes. We'll talk about that later. What's the phase relationship between current and voltage in an inductor. Remember when we got to inductors and capacitors, we said there was a phase shift and one leads the other. We had a saying to remember that. Anybody remember the saying? So it was Eli the Iceman, right? Eli, E-L-I, L being inductor, E being voltage, I being current, and then ice was for capacitor, the C being capacitor, the I was current, the E was voltage. And so Eli told us that our voltage leads current by 90 degrees. Our voltage leads current. The reason that happens, the reason that happens is that, remember that inductor is nothing but a coil. And whenever the voltage is first applied, that inductor opposes the change in current flow with that magnetic field, and it begins to build that magnetic field. And so you get the voltage, you get a building of the magnetic field during the change, and that causes the current to lag behind the voltage. Once the magnetic field is built up, then you get your full current. And so you're going to have voltage, max voltage, ahead of your current. Current, and this is an inductor, current leads voltage. Voltage leads current. E, voltage, current is the I.
Was this given to us the second session? What session was this in?
It would have been when we probably the same session we started talking about alternating current.
Okay.
And when we started talking about inductors and capacitors, right? And so this notion of Eli being L being an inductor, so our voltage leads our current, and it's all because that magnetic field is expanding around that coil of wire. And then for the capacitor, I've got two plates that are going to build up. Well, I'm going to get current flow, and as the current is flowing, it's going to charge up. And so I'll have my charge across that capacitor once it, after a delay. And so therefore I'm going to get current leading my voltage. You can also just remember these two. The inductor, it opposes changes in current flow. It's trying to maintain a steady current. And so it's going to cause the current to lag behind. The capacitor is trying to oppose changes in voltage. And so it's going to cause the voltage to lag behind. But definitely, if you go back and you review, and if you have any questions about that, let me know at a session, and we can go back and hit that again.
Thank you.
Absolutely. A coil across a 500 cycle generator has an inductive reactance of 300 ohms. Increasing the frequency to 1,000 cycles will. All right. So the question here really is, we're talking about an inductor, right? We're talking about a coil, this inductive reactance. And we have to go back and we have to remember what the formula was for inductive reactance. Anybody remember the formula for inductive reactance? Yeah, that was X sub L
divided by E.
So it was X, and we did like this, sub L equals 2 pi and then we said that the size of the inductor was a part of it, right? But there was one other variable here. Anybody remember what that was? 2 pi f. And what was f? If L is the size of the inductor, 2 pi is just 2 times 3.14. F was the frequency, right? And what we were saying is basically that as my frequency increases, the resistive value, this was inductive reactance, which is measured in ohms, right? So that value is directly proportional. And so that's really what this question is getting to. It's saying that if I have a coil across a 500 cycle generator as an inductive reactance of 30 ohms, and I increase the frequency from 500 cycles per second to 1,000 cycles per second, so I double the size of F, what's going to happen to X of L?
Double.
It absolutely, right? If I multiply this side by 2, if it's getting greater, this side's got to get greater as well. So double the inductive reactance, cut the inductive reactance in half, not change or reduce the resistive coil. So it's got to be A, right? Let's see here. Let me do this so that there we go. Very good. All right, let's do 2 more. Given the voltage applied is 12 volts, R1 is 6 ohms, R2 is 4 ohms. What is R total?
C.
Okay. Okay, so 10, if we were in a series circuit, that'd be right? Because you just add those resistors together in a series circuit. In a parallel circuit, right? This is parallel.
2.4.
How much?
2.48. Smaller than small one.
Ah, yeah. Let's not forget that in parallel, the total resistance is always going to be smaller than the smallest. All right. So my smallest resistor was 4. The only answer that works is 2.4. Now the formula, how I would do that, remember I've got a couple shortcuts. I can use the reciprocal of the sum of reciprocals, but since I've got 2 resistors and they're not equal, I can use the product over the sums, right? So I could say, let's multiply those 2 together, the product. So 6 times 4 is 24. Divide that by the sum, which is 10. 24 divided by 10 gives me that 2.4. Yep. I would say if you get a question and you've got resistors in parallel, always take a look at the smallest and know that your calculation, when you finish your math, it should be smaller than the smallest. But since you know that rule of thumb, go ahead and take a look at the answers, because if there's only smallest, you can go ahead and check that answer and move on. All right. So in the circuit shown, what is the total capacitance? Total capacitance. When we were talking about capacitor,
25.
how much?
25.
25
together.
Okay, 25. And when we were talking about capacitors, what I was going to say is, we looked at how we combine capacitors in parallel, and we said that when we combine them in parallel, it's like extending those plates, and that was one of the things that we said would increase the capacitance. It's like making the plates bigger. Absolutely. So 25 microfarads. Very good. Very good. All right. So we are 20 till. I'm going to hang right here. You guys, we're only about 5 minutes outside of your breaks. We're only about 5 minutes early, but I just don't want to go to I want to keep all the computer stuff together for our next session 10. So I'm gonna go ahead and cut you loose. If you got any questions, I'm gonna hang here until top of the hour. So feel free to hang around, ask any questions that you might have. Otherwise, if you want to use the extra 5 minutes you got to go take one of the quizzes, feel free. Have a good weekend, and we'll see you guys on Monday.
Thanks, Mike. So do you.
Thank you.